Now, we make a lot of assumptions when we do calculations regarding buffer solutions. And in making those assumptions, what we can do is we can actually simplify the calculations that are done when calculating the concentrations in the pH in buffer solutions. And this simplification is called the Henderson-Hasselbalch equation. So if you have a buffer containing a weak acid, let's just say the weak acid is HA, generic acid, and its conjugate base, which is A negative, we can use a special equation to help us calculate the pH. Now let's first write the equilibrium reaction for this dissociation or this ionization of this acid. We have HA, generic acid. This is a weak acid. It needs to be a weak acid, and we have that in water, in liquid water. We're going to create hydronium, H3O+, and A-, which is the conjugate base. This is what's left over after we've removed that hydrogen. Now here's our equation. We can calculate the pH by taking the pKa plus the log of the concentration of the conjugate base over the concentration of that weak acid. Now keep in mind, we haven't seen pKa before, but we have seen what we do when we put a p in front of something. We take the negative log of it. So the pKa is the negative log of the Ka, or the acid dissociation constant. Then we're going to take that and we're going to plus the log of the conjugate base, or the concentration of the conjugate base, over the concentration of the weak acid. Now we're able to do this if our Ka is very small, and what that will allow us to do is that will allow us to have a very small x value. So if our Ka is very small, our x value is also going to be very small, and that allows us to eliminate, remember, eliminate those plus x's and minus x's from our ICE table when we did our buffer calculations. That eliminates those x's and just puts this all into one equation that allows us to calculate the pH. So here we have calculate the pH of a buffer solution that is 0.050 molar benzoic acid. This is the weak acid. And then we have another solution in there. It's actually a salt, but it's going to be the source of our conjugate base ions. So we have a 0.150 molar sodium benzoate solution, and that benzoate is our conjugate base. So the pH is equal to the pKa plus the log of the concentration of our base, our conjugate base, over the concentration of our weak acid. So when we calculate this all out, the first thing we need to do is establish what our Ka value is. So the Ka for benzoic acid is 6.5 times 10 to the negative fifth. This is pretty small, meaning that the benzoic acid isn't going to dissociate very much, meaning our x value is going to be very small, which means that we can use the Henderson-Hasselbalch equation. And if our Ka is 6.5 times 10 to the negative fifth, then our pKa is the negative log of this. So the negative log of 6.5 times 10 to the negative fifth is 4.187. So that's our pKa. Now I'm going to plug this into the original equation. So I have pH is equal to 4.187 plus the log of our base concentration. So the concentration of our conjugate base. Now, our conjugate base is the NaC7H5O2. So that's going to be 0.150 moles per liter. And the concentration of our weak acid, so the benzoic acid, the HC7H5O2, the concentration of that is 0.050 moles per liter. So we take our base over our acid, remember the concentration of our base over the concentration of our acid. So what I'm going to do here is just take my answer, which was the 4.187, plus the log of 0.150 divided by 0.050, and I get 4.66. So the pH of this buffer solution containing a weak acid and its conjugate base is 4.66. Let's try one more practice problem. Calculate the pH of a buffer solution that is 0.250 moles per liter HCN and 0.170 moles per liter KCN. So our acid, our weak acid, is the HCN, and the source of our base ions is going to be the KCN. The base ions are going to be the CN minus ions, but you will often find that buffers contain a salt solution as the source of your conjugate base ions. So the Ka for HCN is 4.9 times 10 to the negative 10th. So our pKa is the negative log of this. So negative log 4.9 times 10 to the negative 10th, which equals 9.31 or 9.3098. So that is our pKa value. I'm just going to substitute that in here. 9.31. Now I'm going to add the log of our base concentration, which is 0.170. That's our KCN, the source of our base ions. Remember that potassium is just part of the salt compound, not really a base, but it's kind of just connected to the base there. And the acid concentration is 0.250 moles per liter. So punching this all into my calculator, I add my previous number here, 9.31, plus the log of 0.170 divided by 0.250, and I get 9.14. So our pH, the pH of this buffer solution, is 9.14.